Hello AP Chem students and welcome to Unit 3. Unit 3 is Properties of Substances and Mixtures. It is the largest unit in the AP Chemistry curriculum, and because of that, it is also weighted the heaviest on the AP exam. So it is 18 to 22% of the exam. There are 13 topics, and this is the first one. So topic 3.1 is intermolecular and interparticle forces. So the learning objective for today is 3.1.a, explain the relationship between the chemical structures of molecules and the relative strength of their intermolecular forces when 1. The molecules are of the same chemical species, and 2. The molecules are of two different chemical species. So let's see what we got. So let's first talk about the difference between an intermolecular force and a bond. So intermolecular forces are the forces between molecules that lead to a condensed state. A condensed state is a solid or a liquid. These forces are considerably weaker than ionic and covalent bonds, but they do add up to have significant impacts on molecular properties. So we got a little graphic here that shows you the difference between them. So first of all, remember intermolecular forces can be abbreviated as IMFs, and that is a term that you may use as an abbreviation on the exam. Intramolecular forces are what we call bonds. So intermolecular forces are the forces that hold molecules together in a substance, whereas bonds are what hold atoms together in a molecule. IMFs are weaker than intramolecular forces, so bonds are stronger. So the IMFs help to determine the state of matter, so solid, liquid, or gas, and physical properties such as melting point, boiling point, etc. They also allow us to decide if something is going to dissolve, if two things will dissolve in each other. And we're going to look at that more at the end of Unit 3. They also, whereas bonds determine the chemical behavior of a substance. Will it react? Will it not? IMFs are attractive forces, whereas bonds are just bonds. So with bonds, we have the overlapping of the electron cloud or electrons being given or taken. And we have a different situation going on with intermolecular forces. Hang on, let me pause that. Okay, so then we're going to talk more about the types of IMFs here in just a second. Remember that the types of bonds are covalent, ionic, and metallic, because we're going to talk about those a bit more as well. All right, so just to show you again one more time, between the H and the Cl, we have what's called a bond. Okay, this is a covalent bond. And then between an HCl molecule and another HCl molecule, we have the intermolecular force. And comparing the two things to each other, a bond is much stronger than an intermolecular force. So we have to use chemical means to overcome bonds. We can overcome intermolecular forces physically. So usually we can overcome IMFs by doing something like, say, heating it, okay, or whereas with bonds, we would have to heat it much, 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 much hotter or react it in some way. All right, so then again, intramolecular force keeps the molecule together. Those are called bonds. Intermolecular force is between two molecules, and that's responsible for keeping matter in a solid or liquid phase, which are called condensed states. Okay, so much like bonding, IMFs can be seen as being on a continuum from weakest to strongest, right? There is overlap there, and it really depends on the features of the molecules themselves. Just like with bonds, we saw that the strength of the bonds depends on features of the atoms themselves. But the features of molecules involved will greatly impact the strengths of the IMFs, and we're going to talk about that more here in this topic. So generally the weakest is dispersion forces, and then dipole-dipole is stronger. Ion dipole is even stronger again, and then hydrogen bonding is somewhere kind of in the overlapping here with ion dipole. Then if we want to go stronger, then we would get to the bonds, and that's where we would have covalent bonds and ionic bonds. Metallic is not mentioned here because we're just they're kind of different. We're kind of putting them off to the side, right? Here today we're, and then actually pretty much in most of Unit 3, we're going to just be thinking about ionic and covalent substances. Okay, so we're going to start with London Dispersion Forces, which are the weakest. They exist between two covalent molecules. So remember that molecules have electrons randomly moving within them. At any given time, the location of the electrons can be such that a brief separation of charge can occur. It is fleeting and instantaneous, okay? But it occurs even within nonpolar molecules, creating what we call an instantaneous dipole. So here you go. So if you have two atoms of neon, remember that the electrons are in constant random motion. Okay, so they're constantly appearing, disappearing, reappearing somewhere else. So it can happen that they just all happen to come together on one side for a moment in time. that would create this partial negative that you see down here. Okay, so then that would similarly create a partial positive over there. Well, then that partial positive would attract the electrons of the neighboring neon, and so they would come running over. And then that would set up this partial charge in the neighboring neon. And then that kind of becomes a domino effect. They neighboring neons impact each other. Now, as soon as this happens, it unhappens, right? So again, the electrons are in constant motion. So as soon as one forms, it's going to impact the atom next to it, and then it's going to change again, okay? So this can affect electrons and nearby atoms, which we just talked about, creating what we call an induced instantaneous dipole. This causes an attraction between the partial positive and the partial negative, and that's what we call the London Dispersion Force. Okay, so here's another graphic showing you. So here's atom A and atom B of two helium atoms with no polarization. Here atom A is not polarized, atom B has become randomly polarized, and then that sets up an impact. Atom B then impacts atom A. You can see that here. Atom B has this temporary instantaneous dipole that's partially negative here, and then that sets up this partial positive on atom A. So it's important to realize that the greater the number of electrons in the molecule and the more spread out the molecule is, the stronger the intermolecular forces will be between them, because it gives you more opportunities for these electrons to just randomly have an electron cloud that is unevenly distributed. Okay, so we say that the term that we would use for that is more polarizable, right? So that's the phrase I would like you to use. That is the tidiest way to describe what I just talked about. Atoms or molecules that have a greater number of electrons or are more spread out, more elongated, are more polarizable. And also remember that all covalent molecules have LDFs. And if you are asked to list the intermolecular forces of any covalent molecule, you must also include LDF in addition to any other type of intermolecular force that it might have. All right, so now let's talk about another type of intermolecular force called dipole-dipole. So dipole-dipole interactions are the intermolecular forces that result from molecules with dipole moments attracting each other electrostatically by lining up, okay? So the thing that holds dipoles together is their opposite charges. And so that's what's happening here. So you have this hydrochloric acid molecule, and it's got a partial positive and a partial negative. And then the molecule that is neighboring it also has a partial positive and a partial negative. And so they just naturally orient themselves like this. So that positive, negative, as you can see down here very nicely in the picture. Sometimes this even happens with temporary charges, all right? But once again, we have an application of Coulomb's law, okay? So they are held together by the attraction between them. And as the distance between the dipole increases, the strength of the attraction would decrease. We also have the other part of Coulomb's law that's at play here, the strength as your dipole gets stronger, right? So more partial positive, more partial negative, then we would also expect that dipole-dipole force to increase as well. So both of these parts of Coulomb's law are at play. Okay, so then we can think about a lot of different types of dipole interactions. So first of all, it does this to me. There we go. The partial charge on the dipole can interact with other charges, be they full charges, like in the case of ions, or temporarily partial charges, like in the case of induced dipoles. So these partial charges can interact with the charge on ions, leading to what we call an ion-dipole interaction. So that's what you would see down here. So here's ions, and then here's dipoles, and you can see that they line up. So the negative would line up with the positive would line up with negative, as we would expect. Then this would be a dipole-dipole. Okay, so ion dipole would be stronger because you have a full charge and a partial charge interacting with each other. Again, this Coulomb's law, right? The two charges, the magnitude of the charges. You have a dipole-dipole, so that would be a partial charge and a partial charge. Up here, you have an ion-induced dipole. We would expect that to probably be weaker than a dipole-dipole because an induced dipole is generally not as strong as a permanent dipole. And then we could also have a dipole-induced dipole, which we would expect to be weaker, again, than an ion-induced dipole. So you can see both of those situations laid out here, and then also here. So this is what a dipole-induced dipole looks like. You have a permanent dipole that you introduce into something that doesn't have a dipole, so a polar substance being introduced into a non-polar substance, but it can create this induced dipole-induced dipole. This, by the way, is why you can see things that don't normally mix together might mix temporarily. Okay, we'll get more into solutions later. But for example, you can shake up your salad dressing and it will stay mixed for a little bit of time, but then if you sit on the table and leave it alone, it will go back to being unmixed again. And again, we're going to look at that specific example later on in the unit. And then finally, we have London dispersion, which is temporary dipole, temporary dipole. Okay. So again, just some other examples. We have ion-ion, which we would expect to be the strongest of all of these because it would be a full charge with a full charge. You'd have a dipole-dipole, which is a partial charge with a partial charge. We're going to talk about hydrogen bonds here in just a second. And then ion-dipole, we would probably expect to be in the middle of ion-ion and dipole-dipole. It would probably be kind of in between those because you have a full charge interacting with a partial charge. So when you're comparing the strengths of the interactions of the dipoles and the ions, you want to consider the following factors. Number one, the magnitude of the charges and or the dipole. And number two, the polarizability of any nonpolar species. Again, the more polarizable it is, the more likely it is to form London dispersion forces that are going to be impactful. Okay. Okay, so hydrogen bonds. All right, well, let me move my face over there. That'll be good. Okay, so here we go. So a particularly strong kind of intermolecular force is called a hydrogen bond. This is a terrible name. It is not a bond. It is an intermolecular force. It's a very misleading name. Please remember, it is not a bond. It is an intermolecular force. They occur between a hydrogen atom covalently bonded to a nonmetal atom and a nonmetal atom of a neighboring, and then attracted to a nonmetal atom of a neighboring molecule. So a hydrogen atom is covalently bonded to a nonmetal atom, and then that is attracted to the nonmetal atom of a neighboring molecule. Now, that nonmetal atom has specific requirements. It needs to be small, and it needs to be highly electronegative, and for those two reasons, in this class, we consider hydrogen bonds as only occurring between hydrogen and fluorine, oxygen, and nitrogen. So I want you to remember that hydrogen bonds are fun. Okay. F-O-N. So even though they're relatively weak compared to bonds, they are very important and they contribute to the structure and function of many molecules. And this is so important that the AP curriculum has specifically listed these examples for you. Number one, it gives the structure, the helix structure of DNA. Okay, so the two strands of DNA are held together by hydrogen bonds between, there you go. Okay, TNA and G and C, these are hydrogen bonds in between them. They hold together water molecules in their solid and liquid form, and that is super important, and I really want you to remember that water hydrogen bonds, that's very important for a lot of the features of water and the way that it behaves. And then finally, it gives three-dimensional structure to proteins as well. So hydrogen bonds are really important, especially biologically. Okay, so I just want to point out here that this right here, between this O and this H, that's a bond. Between this O and this H is a bond. Now, this H is bonded to an O, and it's attracted to another O on another molecule. This is a hydrogen bond, which is not a bond. It's an intermolecular force. Okay, here, oxygen molecule, or sorry, oxygen atom. Woo. Here's an oxygen atom. Hydrogen bonded to oxygen, attracted to neighboring oxygen. Hydrogen bonded to oxygen, attracted to neighboring nitrogen. So that's fine because it's F, O, or N. Okay, so the hydrogen must be bonded to F, O, or N and then also attracted to F, O, or N in a neighboring molecule. All right, so here's a lovely summary of intermolecular forces for you. So we have dispersion, which we're going to abbreviate and call LDF, which are the weakest of the intermolecular forces we would expect. Then you have dipole-dipole, then you have hydrogen bonding, and then you have ion-dipole. Now, again, there's going to be some flux here. These are not absolute rankings. For example, London dispersion forces, which are generally regarded as being the weakest of the IMFs, can actually sum up to be impactful. AP exam is not going to ask you to tease out where that line is. It will give you data that will allow you to deduce that fact, and it will ask you to explain it, and you'll be able to explain it in terms of London dispersion forces. And we're going to look at some more examples of that in class. All right, so I do want to talk to you a minute about how this applies to AP questions, because you're going to see this again and again and again and again. Intermolecular forces are not going away, so they're really important for you to learn and master, okay? So, number one, all covalent molecules have London dispersion forces. And you need to state that anytime you're asked to list the IMFs involved in a species. Intermolecular forces can affect the physical properties of molecular structures, of molecules structures. Like so physical properties means like melting point, boiling point, freezing point. Here, I've got it. Melting point, boiling point, enthalpy of vaporization. So in other words, how much energy is required to vaporize it. And then I think I mentioned this already, but we're going to look at it as well in terms of will it dissolve, will it not dissolve, what's it attracted to, things like that. Dispersion forces become stronger with increasing number of electrons and elongation and must be considered in nonpolar molecules. Dipole forces are found in polar molecules, and when comparing substances of similar molar mass, these forces are stronger than dispersion forces. But again, if the molar masses are different, sometimes dispersion forces can be unexpectedly impactful. In ionic compounds, the charge on the ions is what's going to dictate your interactions with neighboring molecules. However, it should be remembered that these ions interact with existing dipoles or neighboring covalent compounds, or they can cause induced dipoles. Okay, so we're going to look at that again moving forward as well. So what should you be able to do with this? Well, number one, you should be able to list all the IMFs present in a pure sample. So is there a dipole? Yes or no? Is there a hydrogen bond? Yes or no? And then, of course, everything covalent has LDFs. You should be able to identify and label the presence of a hydrogen bond. So like I want you to be able to circle a hydrogen bond if you see substances. Compare the strength of IMFs present in a sample. Justify differences in physical properties of two substances based on the strengths of the IMFs present in each substance and atomic and electronic structure contributing to those IMFs. And then use Lewis structures of two molecules to determine what IMFs exist between them and how that impacts their interaction. And that is it for topic 3.1, and I will see you soon for topic 3.2.